Hello dear students, here in this video I'll be talking about infinite square well. And what is it? Basically is that we have a particle and it's a quantum particle, it's a microscopic particle, and this particle is confined, it's confined to the boundaries having infinite potential. And what we presume is we have a particle, and this particle is allowed to have motion along, say, x equal to 0 to x equal to L. So assuming this length equal to L, then this particle is facing an infinite potential at the boundaries of this length. So that the probability of finding this particle outside this one-dimensional box is 0. So we can say that that the particle is confined to this infinite square potential. And to start with, the basic equation that's utilized in exploring the energy of the particle in this infinite square well is the Schrodinger's time-independent equation. So if I write down the second order differential equation for this particle, this will be 2m by h cross square E minus v of psi equals 0. Now we can what we have is that the potential the potential inside this box for this particle is constant. It can be taken equal to 0, and we'll be left with dou 2 psi by dou x2 plus 2m by h cross square of psi equals 0. And here we must have E, and we can write down it as h cross square by 2m dou 2 psi by dou x2 is equal to, keep minus here, E psi. So this is our Schrodinger's time-independent equation, and we will be exploiting this equation for our problem that I have defined. And the boundary condition is defined here, and talking about psi, the value of psi outside this domain is 0, and the value of psi at the position x equal to 0 is 0, and its value at x is equal to L is 0. So the solution of this Schrodinger's equation, we can write down its solution, and the solution will be, say, a sine kx plus b cos kx. So if I think in terms of Schrodinger's equation, dou 2 psi by dou x2 plus k square psi equal to 0. So choosing the solution for psi for this Schrodinger's equation as a sine kx plus b cos kx, where this k is under root of twice m e by h cross square. Now we have a situation like this. We have the particle, and this particle is experiencing it's bound between two infinitely hard potentials, so that this particle has no probability of being present outside this domain. Now if we try to exploit the boundary condition here, say for example at x equals 0, psi will be equal to 0. So we can use this condition, and we will have 0 is a sine 0 plus b cos 0. Now this is 0, so b must be equal to 0, because cos of 0 is 1, so b must be equal to 0. So the wave function will be boiled down to a sine k of x. Now, as we understand that this k, a and b, they are both constants, and utilizing this boundary condition on this wave function, what we obtain is that the value of this constant b is 0, and the value of constant a can be calculated, and it can be calculated using the normalization condition. Now, what is the normalization condition is that what we say is if we have a wave function, we have its complex conjugate, and over this length the probability of finding this particle over this entire length must be equal to 1. Now we can extrapolate this equation to our problem, where we have the limit from 0 to L, and for sine what we have is a sine of kx times a sine of kx, and dx is equal to 1. So this is our complex conjugate. So sine of kx, it will have no complex conjugate. For a, we can have star of a, and we can write down the magnitude of a square, integral 0 to L, then sine square kx dx is equal to 1. So now we can obtain the value of this constant using normalization, and for this sine square kx, what we have is a square. We can think of sine square theta. Suppose I have sine 2 theta. Okay, so sine 2 theta will be, yeah, so this is sine theta plus theta. So this is sine theta cos theta plus cos theta sine theta, right? And so we can have sine theta cos theta. So this will not work here. I think we have cos 2 theta. Cos 2 theta will give us cos square theta minus sine square theta. So this will be sine 1 minus sine square theta minus sine square theta. So what we will have is 1 minus twice sine square theta must be equal to cos 2 theta. So from here, what we can do is we can obtain this this sine square theta. So what will be that? That will be, is it observable? Yeah, it is. So from here we can obtain twice sine square theta is 1 minus cos 2 theta. So sine square theta is 1 minus cos 2 theta by 2. So instead of sine square kx, we can use here twice sine. Oh, sorry. We can use here 1 minus cos 2 kx divided by 2 times dx is equal to 1. All right. So what is the limit of integration is from 0 to L, because the particle is bound between 0 and L. So we can have here a square, and this will give me simply L by 2, and this will have sine after integration, and we will obtain 0 here for this cos of 2kx. This is equal to 1. So a square will be 2 by L, so a will be under root of 2 by L. So using normalization, what we have done is we have calculated the value of this constant a, and now we have the wave function. We can write down psi n is under root of 2 by L, then sine of kx Now we can use another boundary condition. I mean, we have the particle, and this is x is equal to 0 to x is equal to L, and at x is equal to L, what is psi? Psi is again 0. So if I think in terms of 0 here, so using the boundary condition that at x is equal to L, psi is again going to be equal to 0. If that's the case, then we can have this 0 equal to under root of 2 by L sine of kx. And we understand that this 2 by L is not 0, then what is 0 is this sine of kx. So sine of kx is 0, and for sine of kx we can write down sine of n pi, because sine of n pi is equal to 0. So from here we have k equal to n pi by x, but at this limit x is equal to L, so k is n pi by L. So we can write down the wave function for the problem that we have chosen, and what will be the wave function? That will be psi n is under root of 2 by L sine of n pi by L x. So this is our generalized wave function for this particle who is encountering infinite potential, and we can have different values for this wave function. And before proceeding, we can also look for this, if we look for this k is n pi by L. But from the original choice, this k was, it was 2m e by h cross. So for k we can use here, it was under root of 2m e by h cross. So we can use under root of twice m e by h cross for k is equal to n pi by L. And we can have squaring on both sides. So we'll have 2m e by h cross equals n square pi square by L square. So from this equation, we can obtain the energy eigenvalues, and we can see that this particle will not have all possible energies. It can have only, it can exist only in certain energy levels. So we will have E equal to, so we will have n square h cross, then we will have pi square by 2m L square. So from this equation, what is clear is that this particle is not going to have all possible energies. It will have energies corresponding to n is equal to 1, equal to 2, equal to 3, because n is an integral number. So this is one conclusion from solving Schrodinger's wave equation on this particle who is existing between these two this infinite Scarvel potential. Now, writing down, so we can plot down these energies. So we'll have some discrete values of energy that this particle will have. It cannot have the energies between the two values. Suppose we have value A, value B, value C, and value D. This particle can exist in having an energy state of A. It can be in state of B. It can be in state of C. But it can never have an energy between the state of A and B. That's what the equation that we have here is reflecting. Now, writing down the wave function for this problem, psi n is under root of 2 by L sine of n pi by L times x. Now, for different values of n, we can plot this amplitude. We can plot this amplitude with respect to the position. Now, say for example psi 1. So for psi 1, we have a plot like this. And what we assume, we don't assume these 2 points as the nodes, but if you take psi 2, in case of psi 2, you will have one node, but the end points are not considered as nodes. Then psi 3, you will go on adding a node for the more generalized excited wave functions. So this way, now we can have the wave function. The state of the particle can be psi 1, it can be in some higher state psi 2, it can be in some higher state psi 3. Now, in order to exploit the situation here in terms of the wave function, suppose we have some state as psi m star and some ground state as psi n dx. Now this is, if this integral for the given problem, say if I choose it from minus infinity to infinity, if this integral comes out to be 0, then we say that this wave function is, these wave functions are obeying the condition of orthogonality. Now let us check this orthogonality for the wave function that we have obtained for the particle in this infinite Scarvel potential. And so for that, we will have psi n. And what is psi n? That is under root of 2 by L sine of n pi by L x. And choosing some other state, psi m star, that will be under root of 2 by L sine of m pi. Instead of n pi, we will use m pi by L x. Now, using these two wave functions, these two state vectors in the left-hand side of the equation, and using the boundary condition. So what will it look like is integral 0 to L, then you will have under root of 2 by L, then you will have under root of 2 by L, then you will have sine of m pi by L x, then you will have sine n pi by L of x, and then you'll have dx. All right, and we can get this out, and here we can use twice sine theta, sine of theta 1 and sine of theta 2. So we can use that formula over here, and what we will obtain is, we will obtain 1 by L integral 0 to L, and you will have twice sine of m pi by L x and sine of n pi by L of x dx. So we can boil down this integral, and we can use the formula as twice sine theta 1 and sine theta 2, and what we'll obtain here is this is L, what we obtain after integration. So because we will have here, we can write down it as cos of m minus n times x, and then here we will have cos of m plus n by L of x. Suppose we have not integrated it yet, then close it to dx. And then once we integrate it, what we'll get is 1 by L, and then you will have integration of cos will give you sine of m minus n by L of x, divide by m minus n of L, minus sine of m plus n of x by L, divide by m plus n by L. All right, so the limit of integration will be from 0 to L. Now if we look at the body of this the solution that we have obtained here, for m not equal to n, this whole thing is going to give us 0. So this is indicative of the fact that the wave function in the state n and the same wave function in the state m, they are holding the condition of orthogonality. For m is not equal to n, the integral that we have written down, that integral is equal to 0. So on the other hand, so what we have done here in this problem till now, we have obtained normalization, and what was the, so for normalization you have a condition of getting 1, and then you have orthogonality, and for obtaining this orthogonality between the two different states of the same function, you obtain 0. So we can absorb both of these results for a particular situation in a compact form, and what we can have is, we can write down integral minus infinity to infinity, then sine m of star and sine n of dx is delta nm. So this equation is called a Kronecker delta function. And it certainly takes care of both the situations that we have been talking about. So for normalization, what we have this the value of this integral is equal to 1, and for orthogonality, the value of this integral is equal to 0. So using a Kronecker delta function, we can incorporate both the states of the measurements that can be carried out on this particle in terms of normalization and orthogonality. So in combination, we call this process as orthonormality. So for normalization, this delta nm will give us 1, and for orthogonality, this delta nm will give us 0. So what is condition here for normalization is that you're talking about the same wave function in the same state. So here n is equal to m, and here in case of orthogonality, this n is not equal to m. So the things that we obtain over here, they are strange, because if we think classically, the particle must have all possible energies. It must have all possible energies in this infinite square well. But when we treat this particle quantum mechanically, what we obtain is, we obtain that it has energy eigenvalues, it has energy, it has quantized energy. It cannot have all possible energies.